Okay, so what we're going to do today is we're going to take a look at calculating equilibrium constant from partial equilibrium stuff. And remember, we always said is that there's two problems they can give you. They can either ask you to solve for the equilibrium constant and give you a bunch of equilibrium stuff, or they can ask you to solve for the concentration and they can give you the K value. In this case here, they're asking to solve for the K and they're giving us stuff. So let's go take a look at the actual problem. And there's a couple things that we note here. One is they're asking us to solve for the Kp. And that's important because when we take a look, normally if they asked us to do a problem with concentrations, we would see either molarity or we'd see like moles and volume. But in this case here, all we see are atmospheres. So first things first, they tell us that ammonia is going to decompose into nitrogen and hydrogen. We should write an equation for this just so we know where we're going in this problem. So I'm going to write it out first. And it's kind of the backwards of one that we use all the time. This is a gas, and we can just kind of follow the wording of it here, and it's going to be at equilibrium with N2 and H2. And these are all gases, which means that we can do a Kp for it. The other thing to bear in mind is that we have to do the correct coefficients for each of these, and so to balance this I'm going to have to put a 2 right here and a 3 right here. So that allows us to then write our K expression, which I'm going to write right away so we have it at our disposal. And the K expression is going to be Kp is equal to the, remember it's always the products raised to their coefficients all over the reactants raised to their coefficients. But since it's a P, we're going to write the P first, and so the first one's going to be Pn2, and we're going to multiply that by P H2, but the H2, because the coefficient right here is a 3, the exponent we're going to have to put right here is 3, and all of that is going to be over P NH3 squared. Now, where does that impact us here? Well, it impacts us in our ice problem, and we're going to do an ice problem just like we normally would, but I will point out a couple of pieces of information here. They tell us in this problem that they're starting us off with 3.6 atmospheres of this guy right here. And then they say this, and this is really, really important. They don't give us any other information at the beginning, so we can go ahead and write this down and go, all right, let's bank this 3.6 ATM right here. But then the only other information they give us about anything is they say, oh, by the way, at equilibrium, the nitrogen gas is 1.1. So we know that down here, at equilibrium, we're going to be 1.1. Now remember, we have 0 here and 0 here to start with. But I made the 1.1 here. I really mean it to be over here and the N2. So let's just go ahead and do our problem. And we're going to go, we start off with 0 of this and 0 of this. Now, I would suggest until you get really comfortable just treating everything like you normally would with x's. And since we have a coefficient of 2 in the front, we're going to be able to go, all right, this is going to be minus 2x here. It's going to be plus x here, and it's going to be plus 3x here. And at our equilibrium, we're going to have 3.6 minus 2x, we're going to have x, and we're going to have 3x. Now, if we were to plug all of these values back into our equilibrium expression, so if we take these and we're going to plug this guy into here, and this guy into here, right? And then this down here, everything would be great, except we don't know what x is, or do we? Didn't they tell us right here that the nitrogen gas was equal to 1.1 ATM? So isn't x at equilibrium, isn't that N2s? And wouldn't that be equal to 1.1 ATM? So that's kind of really, really helpful because we know that the x here is equal to 1.1 ATM. So if that's the case here, wouldn't this be 3 times 1.1? And wouldn't this be 3.6 minus 2 times 1.1? And so we can plug all these variables back into our equation straight over here. And if we were to put it in with x's first, and I'm going to grab this whole thing and just lasso it and bring it down here just so we have a little more room. Let's say we have this right here, and we're going to plug these variables in. On the top here, if I were to write it out, I'm going to end up with x, and here I'm going to end up with 3x cubed, and on the bottom I'm going to write 3.6 minus 2 times 1.1 in here, or just 2x, however you want to do it, right? Then all of our values here, we're going to plug back in with this 1.1 equal to x. So wouldn't that be 1.1? And then wouldn't it be 3 times 1.1 all cubed? And all of that 3.6 minus 2 times 1.1 here on the bottom. And this whole thing would be squared. I forgot to put the square here. So when I actually do the math on this, we end up with Kp equaling 20.17. Now, often they tell us what they want us to do for significant figures, and here is no exception. They want us to round to 2 significant figures. Now, if we take a look here, that's really the way we should, because isn't there 2 significant figures here in the problem and 2 significant figures here? There's 3 here, but we're always going to use the least number. So when we finally do our answer, we're going to have to cut it off right here, and our answer is going to be Kp is equal to 20. Decimal. Hopefully this has been helpful.